you're not just throwing stuff at you. I mean, it's not the case of I, C, B, S, T. It can be shown that you know, we actually do the details. So okay, so put this term here, plug it into here, and you will get this equation. Right? So I ask you to do that for homework. That's not too hard. Now here you may notice here we've got an EM naught, and here we've got a Hamiltonian operator. Now this is the same, right? That and that are the same. So where did this come from? This eigenvalue, when here you have an operator. Well, basically it comes from here, right? Because in the case where it's U naught, you've got an eigenequation. So where you did have H naught, UM naught, so you have an M here, so you'll have an EM from this equation. That's where this comes from. Okay, that may help you a little bit deducing this. Okay, so now we've got this equation, and we'll use that again. So I've labelled it. Now it's just plus circle. That's the ID for this equation. Now next course that I do on computer theory, I will probably abandon using this kind of thing, simply because there are just too many equations. I think I'll just use the original equation number as in the text, and it'll probably be easier to follow, if you're reading the text and doing these lectures together. That will make things easier, make the correspondence between the text and the lectures easier. Alright, okay, so look at this equation that do for homework, and then now multiply on the left hand side, on the left of the left hand side and the left of the right hand side by UN0 star. Right? And now if this is a complex function, remember starring it just means conjugating it. In other words, whenever in that function, that term, wherever there's an I, complex number, in other words square root of -1, just put minus I. Right? So that's all that means. Okay, so multiply both sides on the left by this, and then integrate over, well, what would it be? Well, it depends on the context. If it's one-dimensional, it would be dx, integrate dx. If it's three-dimensional, integrate over the volume, the allowed volume, blah blah blah. Alright? Now these U naughts, they remember we said here they are orthonormal, right? So if you're multiplying this and integrating, and the M and N are different, well, they're orthogonal, right? So they'll disappear. So this whole term here will drop out because of the orthonormality of this, when M and N are different. Okay? So when M and N are equal, so you see you've got an N here and an N here, and you're multiplying by UN. Now these eigenfunctions here, the basic ones, to 0, they are orthonormal. Now remember, ortho is short for the ortho is orthogonal, and the normal is short for normalized, right? So so this times this integrated just gives you 1. Okay? So that this drops out, and you just left here with just this term, and that's great. Look, we now have a formula for the first order correction of the eigenvalues, the eigenenergies. Right? So we now have a formula for this. Okay, and that's very useful. We now have a correction to the eigenenergies for our new system, our perturbed system. We now know what the allowed energy, discrete quantized energies are. Very nice. In terms of, well, these terms. So, now this term will drop out, remember, when m and n are different, and you'll, just you got this. So when you have un, and m and n are different, and you integrate, that'll drop out. And you have this term here, when m and n are the same, so you'll get a 1 because of that. But if m and n are the same, this drops out. So the whole, in other words, this whole term, for two different reasons, you know, the orthonormality of m and n here, and the other reason, when m and n are equal, this term drops out, becomes 0. So the whole thing, for all cases, for when m equals n, and for when m does not equal n, this whole term drops out. Okay? So you're just left with this, in effect. So you have, so this en is in fact a diagonal term, if you think about it, of it's a term, one of the terms, the elements, in a diagonal matrix, right? Now it's H dashed, remember? That's the perturbing term in your Hamiltonians, the extra term that you add to your H naught hat, right? Here it is here. But, so to find, so here, now you've got a kind of recipe now, and we'll use it in what, 2 sessions from now in applications. So you now have a formula, it's this one, for the first order correction of the eigenvalues, the eigenenergies. So it's just you know, H dash NN. So this is just one of the term in the diagonal of a diagonal matrix. Okay, and 3 bars here because if you multiply on the left by UN star, here it is, and then you integrate. Right? So here's your formula for the first order error corrections. So what you do is you take your perturbing Hamiltonian, right, operator here. You take the unperturbed or pre-perturbed, unperturbed eigenfunctions, u naught, okay, and multiply on the left of the operator conjugated by un, and on the right by un non-conjugated, integrate over the whole thing, and that is the formula for this, which is this. Okay. So so in other words, this correction term is just found by looking at the diagonal terms, you know, diagonal matrix, right? It's a diagonal matrix of this more general matrix, right? Mn. So you can find a, if you like, a kind of perturbation matrix, if you like. In fact, you only need the diagonal terms, right? You don't need these. Well, here there'd be. Well, let's say the number of n's is big N. So this matrix would be a big N squared matrix. But you're only using the diagonal terms, so there'd just be n of them. So, right? So, if you know the unperturbed eigenfunctions here, you know the perturbing Hamiltonian, you know, the extra term that you add, right? So if you know these two things, you can then find the correction term to the eigenenergies, right? So E1. And so if you let lambda be 1 then you have a correction term, you know, the E1 here, that you add to this, your basic eigenenergies, to get this, right? And we can do similar work to, it gets a bit more involved. We won't do it here. This is just an introduction. It's an introductory course, but you can do this similar type analysis. You can find the second order correction, and so on. Alright, so if you know this and you know this, you can find the first order correction to your energy. So we got our first solid result from perturbation theory. We found a way to calculate the first order changes, corrections to the eigenenergies, and you do it by integrating the perturbing Hamiltonian, H dashed, with this expression where these are the eigenfunctions of the undisturbed, the non-perturbed, if you like, Hamiltonian. Okay, the zero here. Okay, I'll